Hi, everybody. In this section, we're going to start looking at quadratic functions. So we've seen them a little bit already, but we're going to keep going with them a little bit more systematically and looking more at their graphs. So a quadratic function is a function of the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not zero. So a not being zero just means that you actually do have a square term there as your highest power. We've seen quadratics already, so we have learned how to solve quadratic equations, right? We use things like the factoring method and the square root property. We looked at the quadratic formula and completing the square. So we've seen quadratics already, but now we're going to focus a little bit more on their graphs and looking at them in the function form. Now, the graph of any quadratic function is called a parabola, and parabolas are U-shaped. So the ones that we're going to focus on are going to be the ones that are upward facing and the ones that are downward facing. You can have sideways facing U's as well, but those are not functions. They would fail the vertical line test. So that's why we're focusing on these two styles here. They actually are really, really helpful. There are a ton of applications that can be modeled using quadratics. And one of the most popular and common are projectiles. So anytime you have an object that is thrown, hit, or kicked, then this is typically modeled by a quadratic. So if you think about throwing a baseball or dropping, I don't know, something out of your hand, even just letting it fall, that's modeled by a quadratic as well. So, or a rocket. So there's a lot of different kinds of projectiles here that we can use. And the ones that work are the ones where, so when I talk about rockets and things, they would have the initial kind of either being hit or thrown or pushed or something. And then the rest of the energy is just kind of on its own. It just follows that natural kind of path of going up and then falling. And we'll see some of those examples later on. Now, we can tell what kind of graph we have pretty quickly by the leading coefficient. So the leading coefficient is the first number that you see. It's going to be the A here, this one right here. And if that A is positive, then what happens is your graph is going to open up. And if your A is negative, then your graph ends up opening down. So you have those two general ideas here. We also have a point called the vertex, also a turning point. We always label it H comma K, and it's either the lowest point or the highest point of the graph. And then we also have the axis of symmetry, along which we have that nice mirror image. So let me just kind of draw what this would look like for you a little bit bigger here so you can see. I'm not going to put it on a grid. I'm just going to kind of draw them in general. So if your A is greater than 0, then your graph looks something like this. The point here, this is typically labeled H comma K. This is your vertex. So when your A is greater than 0, your vertex is at the bottom, and this ends up giving you the lowest point on the graph. And then that axis of symmetry runs right down the center of the graph. So this line right here is called your axis of symmetry. And it's always the line x equals h. So whatever your h value is, let's say that center point here is at 2, 3, then that line of symmetry runs right along x equals 2. So it's whatever your h value is. And at this point here, you should be able to fold the graph in half, and both those sides would perfectly match up. Let's zoom out a little bit. Okay. If your A is less than 0, then your graph is going to look like this. Your vertex would be here instead. And in this case, it's going to be the highest point. And then right down that center here, that kind of splits the graph in half, you have what we call the axis of symmetry. And it's still always the line x equals h. Now remember, lines of the form x equals are always your vertical lines. So that's why it's x equals. And then h is just that same value here in the vertex. So it just kind of gives us that split of the graph where you have that mirror image on either side. And the nice thing here is that all quadratics look like this. Now they could be moved anywhere on the grid. Sometimes they're centered at 0, 0, other times they're not. It just depends on where the vertex is, but they all kind of have that same general shape. So it's really nice because we can get a lot of information right away from the equation usually without even having to do that much work. Now there's different ways to write quadratic. So we saw one form up here where you just had the squared term first, then the x term, and then the constant at the end. There's another way to write it, and this is typically called vertex form, where it looks like this. And the reason we call it vertex form is because you're able to pick up the vertex very quickly. So that h and k value right here give you that vertex point. And then that a value that's out front is the same a that we saw above. So it's actually the same exact a value, and it works just like it does here. If a is greater than 0, it goes up. And if a is less than 0, then your graph goes down. You saw that same axis of symmetry. So it's just a different form to write the quadratic in, and it can be really nice because, like I said, you can pick up that vertex right away, you can pick up the a right away, and then you can pretty much draw a very quick graph without having too much information. So it's really nice that you can see a quick visual. So how do we draw a graph of a quadratic in vertex form? So first of all, you're going to figure out if your graph opens up or down by using that a value. The most important point of your quadratic is your vertex. You really need to know that lowest or that highest point. Then you can find extra points. So usually points that we find are the x-intercepts, and we solve it by setting the function or y equal to 0. These end up being the real zeros of the function. And then we also usually like to find the y-intercept by setting x equals to 0. So remember here, x equals 0, here y equals 0. And then we can always find additional points as needed. So if you need to find a couple extra points because maybe you're not quite sure of how the graph looks, then you can always plug in different values. So maybe pick x equals 1 or x equals 2 or -1, whatever you want to do to plug in and get some extra values as well. All right, so let's try an example here. And this is in vertex form because I do see we have that parentheses. So what I'm going to do to start is I'm actually just going to write the general form right above it, because I think that'll be helpful for us to see so we can match up the different parts. So this is the vertex form. So that outside multiplier here, that's your a value. So our a here is -2. Your h matches up here. Notice that there is a minus sign, so the h is going to be 3. And then your k is that end value. So I have both pluses here, so k is going to just be 8 in this case. Okay, so let's kind of go through that checklist on the page before. The first thing that I really want to look at is my a value. So I know my a is -2, and this is clearly less than 0. So if my a is less than 0, I know my graph is going to look something like this. The second thing you really want here is you do want that vertex, and it's always h comma k. So my vertex here is going to be 3, 8. So my vertex is going to be this point right here, right at the top. Now, the next thing they want us to find would be any x or y-intercepts. So let's do our x-intercepts first. So for your x-intercepts, you let the y value be 0. So here, what you do is you set your function equal to 0. That would be the same idea. So I look at -2, x minus 3 squared plus 8 equals 0. Now, this is a pretty complex function, but we can go through this and solve. So there's different ways that you can do this. One thing that I'm noticing is that my x is in a square here. So I'm kind of thinking back a chapter ago and thinking, well, I could probably use that square root property here because all my x's are being squared. If you don't like that, you could actually square everything out and use something like the quadratic formula instead, or see if it's factorable. So let's use this strategy, the square root property. I'm going to start by bringing the a to the other side. And then I'm going to divide by the value out front. So I have x minus 3 squared is equal to 4. Now remember that square root property says that you can take the square root of both sides. And you just can't forget you do need a plus or minus there. So I have x minus 3 is equal to plus or minus the square root of 4. The square root of 4 is 2. So here would be my two options. X minus 3 equals positive 2, and x minus 3 equals negative 2. And then if I solve both of those, I can get my final answers. Here I'm going to add 3 to both sides, and I get x equals 5. Here I add 3, and I get x equals 1. So my x-intercepts then are going to be 5, 0, and 1, 0. It's over a little bit. There we go. And then the fourth thing they want us to look for are the y-intercepts. This part's usually a lot faster. So for the y-intercept, you're plugging in x is 0. So you're looking at f of 0 here. Zero minus 3 is just negative 3. Make sure you follow the order of operations. We're going to square first, which is 9. Here I have negative 18 plus 8 and negative 10. So my y-intercept is going to be 0, negative 10. All right, so let's start with that. That's quite a lot of points here already. Right, I already have 4 points. I have 2 x-intercepts, I have a y-intercept, and I have my vertex. And I also know the general shape. So let's start graphing. And then if we feel like we need more points, we can always plug in other values if we want. All right, so I'm going to start with my vertex at 3, 8. Okay. I have x-intercepts at 5 and 1. And then I have a y-intercept at negative 10. And I do know that it looks like this. So if I know the general shape, I can see how it's going to connect. And I'm going to just do my best to try to, oh, that's a terrible one. Match that shape. You guys get the idea. It's supposed to be a nice U shape here. All right, that looks a little better. So that's what my graph is going to look like here. That center, so right down the middle, that axis of symmetry is going to be at x equals 3 because it matches whatever the x value is here. So you should have a mirror image on either side here. Again, I am freehanding the drawing, so I apologize. It's not perfect looking, but you can see some symmetry, right? I see that I have 2 spots here on the left and then 2 spots here on the right from that center for my x-intercepts. So you should have symmetry the whole way down. I'm going to be the same thing here. If you see 3 spots to the left here, then your next point is going to be 3 spots to the right on this side. So you're going to have perfect symmetry all the way down with these quadratics. And if you need extra points, you can always find extra points. So for instance, maybe you want to plug in x equals 2. So if I plug in x equals 2, I just plug it right into my equation here and just keep simplifying. So you can find extra points as you need to. Why don't we do it one time? I won't do it for every single one, but let's say you do want an extra point. You can pick any value you want to plug in. I like to pick x values here. It's going to be much easier than trying to pick a y value. This is pretty hard to solve. 2 minus 3 is negative 1. Negative 1 squared is 1. So I have negative 2 plus 8, which is 6. So again, if I want an extra point, I have 2 6 here. And if I look on my graph, let's see, I have 1, 2, and then 6 would be right here. So that looks good. There's another point. So we can find as many extra points as we want to. All right, let's do another example in this form. Okay, I'm just going to rewrite it over here because I used up a lot of space before. And the general form is ax minus h squared plus k. So that's going to be that vertex form. We're going to start matching things up. If you have nothing on the outside, there is something there. There's always a factor of 1 that we can multiply. So you do have an a value here. Your a is going to be 1. Our k value is pretty easy to see also. So I see k and positive 1. And then just be a little careful here. So your h and your 3 are going to match up. Now you're supposed to have a minus sign in the formula. So what happens is your H value is not going to be 3. It's actually going to be -3. And the reason that would work is because the inside is actually X minus -3. So you have that minus sign that matches, and then to make the plus sign there, it'd have to be a negative number. So when you see that you're matching up a formula and you have the wrong sign, typically you're just going to make that number negative, and that will fix it for you. All right, so my A is 1, which means my A is greater than 0. So I'm going to have a graph that looks something like this. My vertex is of the form HK. So it's going to be -3, 1. And remember, that's your point right here. That's that vertex right there. The next thing they like us to look for would be the x-intercept. And then you're setting that y equal to 0 here. So what you're doing in this case is you're setting your entire function equal to 0. So I'm looking at x plus 3 squared plus 1 equals 0. This is one, again, I really like that square root property here. So if you can isolate the square part when you're in this form, it's usually the easiest way to solve for this style. I take the square root of both sides, and I have x plus 3 on the left equals plus or minus the square root of -1. But the square root of -1 is actually I, right? We saw that already. So when I continue solving here and I subtract 3 from both sides, I get that my x-intercept is -3 plus or minus I, or my two x-intercepts. So what happens here is that they're not real, right? Obviously, they're complex. So if you don't have any real x-intercepts, there are no real x-intercepts here. Okay, so we're not going to see any x-intercepts on the grid. That means that our graph is going to probably be above the axis. It'll either be above or below. Because we're going up here, in this case, it's going to be above the axis. And then we also want to check our y-intercepts. So that's when you let x equals 0. So we're going to plug 0 into our function. We get 3 squared plus 1, which is 9 plus 1, or 10. So we have 0, 10 here. So let's graph what we have. Again, I'm going to start with my vertex. So my vertex here is -3, 1. I don't have any x-intercepts to graph, and my y-intercept is at 0, 10. So up here, 5, 6, 7, 8, 9, 10 would be right there. Now I only have 2 points, but I do know that my shape looks like this. So that actually is enough to graph. I mean, maybe it's not perfect, but I know my graph is going to look like this, and then it's going to be like a mirror image on the other side. So you have that axis of symmetry kind of going right through that center here at -3. Now, once I have that axis of symmetry in there, you can also use that. So here, if I'm 3 spots over, then here I'd be 1, 2, 3. So actually my graph should be a little bit wider because it would match on both sides. Now, if those 2 points are not enough for you, you can always plug in extra values. So if you're kind of like, oh, that's not really enough points, do what we did up here, pick a couple extra values to plug in that you haven't found yet, and find a couple more points on your graph. And then you'll be good, and you can feel a little more confident that you have the right shape. Again, notice here we don't have any x-intercepts, right? It doesn't touch the x-axis because my x-intercepts ended up being all imaginary numbers, so we don't see them on the graph. Your real zeros are what you actually see as your x-intercepts. So if you get imaginary answers, there are no x-intercepts on the graph, and that's why you're seeing this graph in this case above the axis.